The arrival of an object from beyond the solar system caught astronomers by surprise, but that doesn't mean that they were unprepared to study it. The track of our first known interstellar object, now named oumuamua, as it passed through the inner solar system in late 2017, Brookspace SOESD Publication Services Unit. If Hawaii, when the first known object from interstellar space slipped through the inner solar system last month, the welcoming party wasn't quite ready. It passed within 0.25 astronomical unit 37,600,000 kilometers of the Sun on September 9, yet it wasn't discovered until October 19. But in the weeks since, astronomers have more than made up for the celestial slight, marshalling telescopes around the world to learn as much as possible about this interloper before it slips out of visual range, never to be seen again. The flurry of activity hasn't been limited to making observations, as officials at the International Astronomical Union struggled with what to call this body. At first astronomers thought it was a comet based on its extreme orbit, and so the IU's Minor Planet Center applied the designation C2017U1. But when even the deepest telescopic images revealed no hint of a coma or tail, they decided it must be asteroidal, so the designation morphed to A2017U1. What does oumuamua really look like? This artistic portrayal of the object, 2016 WF9, shown passing Jupiter's orbit, might provide some clue. NASA JPL behind the scenes, in an unusual effort to name the new object, quickly emails zipped back and forth among the IU's General Secretary, its Division F President, co-chairs of the IU's Working Group on Small Body Nomenclature, and the Minor Planet Center. The chosen name, announced November 6, is oumuamua. Coined by Ka Tukamura Imura Astronomy Center in Hawaii and linguistics expert Larry Kimura. It's a Hawaiian construct combining out to reach out and mua meaning first or in advance of the second mua as for emphasis. But asteroids are not catalogued by name alone, and this is the first of an entirely new class of object. So, at the suggestion of MPC Associate Director Gareth Williams, the IU adopted the identifier I for interstellar. All parties involved in the discussion agreed that the proposal was suitable, he says. Took less than a day to sort out. Announcement followed the day after. As noted in the announcement on MPEC 2017V17, correct forms for referring to this object are therefore 1I1I2017U1 1I oumuamua and 1I2017U1 oumuamua. Those who work the comet and asteroid trade aren't enamored with the use of I. After all, the IU has gone out of its way to avoid using I and O in designations because they look too much like the numerals 1 and 0. Several have suggested substituting E for extrasolar instead, but Williams defends the IU's decision, noting that E could be interpreted as extraterrestrial, with the implication of intelligence behind the object, and G for galactic is too limiting. A moving target. The first characteristic that marks oumuamua as being from outside our solar system is its orbital eccentricity, 1.19. If you ever took geometry, you might recall that the eccentricity of an ellipse can't exceed 1.0. In fact, dynamicist Bill Gray Project Pluto regrets that he didn't pick up on his interstellar nature a few days sooner. His orbit calculation software kept rejecting the eventual solution as being impossible. The object had already dimmed to 20th magnitude by the time the Pan-STARRS 1 telescope swept it up, so observers worldwide had to scramble to get major facilities to gather more observations before the one-of-a-kind interloper becomes impossibly faint. One lucky break came immediately after the MPC's initial announcement. Observer Joe Masiero Jet Propulsion Laboratory just happened to be in the middle of a run with the 5 meters Hale telescope at Palomar Observatory, and he quickly obtained a spectrum that's reproduced below and explained in more detail here. There's no obvious absorption that would signify the presence of particular compounds or minerals. A spectrum of oumuamua 1I2017U1, acquired on October 25, 2017, with the 5 meters Hale telescope. Vertical bars indicate error bars at each measured wavelength, and the dotted line shows the overall trend to slightly brighter red and near-infrared wavelengths. Joseph Masiero, but the gentle slope, increasing toward the red right end, suggests that oumuamua is not a particularly good match to objects in the Kuiper belt which tend to be much redder. Instead, it's the kind of spectrum that a rocky surface would exhibit after being weathered by long-term exposure to space radiation. Others have attempted to record the object's light curve and determine its rotation period. Observations by Matthew Knight, University of Maryland, and others show clear variations in the apparent brightness of about 1.2 magnitudes. Knight and his team suspect the object is highly elongated, at least 3 times longer than it is wide, and rotates with a period of between 3 and 5 hours. The Hubble Space Telescope might have the final word on the character of oumuamua. A team led by Karen Meach, University of Hawaii (I) has been granted HST time to study the quickly disappearing interloper. Our observations have not executed yet, Meach says, and the experiment requires 3 visits, the last of which will be at the end of the year. And, of course, there's been a flurry of speculation about where oumuamua came from. Dynamicist Eric Mamajek Jet Propulsion Laboratory points out that the object's incoming velocity, 26 km per second, is within 5 kms of the mean galactic velocity of stars that lie within 25 parsecs 80 light-years of the Sun, but it does not match the relative velocity of any of the dozen nearest systems. These characteristics all suggest that oumuamua has been drifting among the stars for a very long time, perhaps billions of years.